Hey guys, today we're going to do 5-7, the binomial theorem. Our objectives are to expand a binomial using Pascal's triangle and to use the binomial theorem. You can use a pattern of coefficients and the pattern a to the n, a to the nth minus 1 times b, a to the nth minus 2 to the second times b to the second, and so on. So we are going to write the expansion of that binomial as a plus b to the nth power. So we can expand a plus b to the third power using the distributive property, where we do a plus b times a plus b times a plus b. And we could also then get a to the third plus 3a squared times b plus 3a times b squared plus b cubed. To expand the power of a binomial in general, we first multiply as needed, then write the polynomial in standard form. But we can consider the expansions of a plus b to the nth for the first few values of n. So if we have to the 0 power, we would expanded form would be 1. Then to the first power, we would have 1 times a to the first power plus 1 times b to the first power. And if you keep looking down, we have the coefficients only from these expanded forms listed here. And these coefficients create Pascal's triangle. So Pascal's triangle starts with a 1, and then it is 1, 1. Then 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. So every row starts and ends with a 1. Then, in order to get the next row, we would add the 2 to get the number below. Add the 2, add the 2, add the 2. So necessarily don't have to memorize this, you just need to know the pattern. We are going to use this in order to expand binomials. Notice that we start at row 0 and we go down. So this would be row 1, row 2, row 3, row 4, and so on. So using Pascal's triangle, what is the expansion of a plus b to the 6th power? In order to use Pascal's triangle, we are going to use the coefficients from row 6. Then we are going to take a and start it at power 6, going down. And we're going to take b and start it at power 0, going up. So, row 6 coefficients are here. 1, 6, 15, 20, 15, 6, 1. So 1, 6, 15, 20, 15, 6, 1. Gonna move those over a little. Now we're going to take our first term in our binomial, which is a, and start it at the 6th power. Then we'll go down to the 5th, a to the 4th, a to the 3rd, a to the 2nd, a to the 1st, a to the 0. Then we'll start our second binomial, b at the 0, b to the 1st, b to the 2nd, b to the 3rd, b to the 4th, b to the 5th, b to the 6th. If we have a positive in our binomial as our sign, all signs are positive. And we can simplify. We don't need to write the 1 and the b to the 0 power, so we would just write a to the 6th plus 6a to the 5th, b to the 1st, plus 15a to the 4th, b squared, plus 20a to the 3rd, b to the 3rd, plus 15a squared, b to the 4th, plus 6a to the 1st, b to the 5th, plus 1a to the 0, we don't write, b to the 6th, would be fully expanded. So that's what the binomial theorem is saying. And now let's do, what is the expansion of 3x minus 2 to the fifth? So we're going to use our binomial theorem. So we're using the fifth row of Pascal's triangle. If we go back to Pascal's triangle, we can see that the fifth row is 1, 5, 10, 10, 5, 1. So here I'm going to write 1, 5, 10, 10, 5, 1. Then I'm going to take my first term and start it at the fifth power. So 3x to the fifth, 3x to the fourth, 3x to the third, 3x squared, 3x to the first. 3x to the 0 is just 1, so I don't need to write it. And then we'll take 2 and start it at the 0, and then 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. Since this is negative, we're going to have opposite signs, so it's going to be positive, negative, positive, negative, positive, negative. Then we need to evaluate, so 3 to the fifth power times and x to the fifth power. 3 to the fifth power is 243. X to the fifth minus, now we have 3 to the fourth times 2 times 5, which is 810. X to the fourth plus 10 times 3 to the third times 2 to the second, is 1,880. X to the third minus 10 times 3 to the second times 2 to the third, which is 720 x squared, plus 5 times 3 to the first times 2 to the fourth, which is 240 x, minus 2 to the fifth, which is 32. So that's the expanded version of this binomial. You guys try number 1, and see you tomorrow.